So we're going to start with the introduction, some history behind IWFM. So you might find this interesting, but the origins of IWFM goes back to 1970s, as I was telling you. That would be my first slide. So this Korean student, Yang Yoon, who was a PhD student at UCLA, basically puts together a finite element groundwater model, and his main reason for that is he wants to develop an inverse modeling approach like PEST that we use. So this is 1970s, this is pre-mod flow days, so there aren't like a whole bunch of models flying around.
Wait a minute, finite difference exists from 1964.
No, I'm not.
It's just dumbing down PC, so that code existed decades before.
Okay, but they're okay. How about this? They weren't as widely available as they are today, right? I mean, mod flow didn't exist. Yeah, I'm not saying that finite element or finite difference methods didn't exist. It's just that, they were, he had to write his own code. And then he graduates and he goes and starts working for consulting companies, Tetra Tech, Boyle Engineering, and between 1979 and 1983, he starts using this groundwater model he wrote for different basin-wide applications. And between 87 and 1990, the model starts becoming really popular. They actually name it Integrated Groundwater Surface Water Model. You might have heard about it, IGSM. And they start basically, applying at different basins, and they include stream routing and land surface processes. And most notably, they basically apply it to California Central Valley. The model is called at the time CVGSM, and that was a part of Central Valley Project Improvement Act, CVPIA. And after this, IGSM becomes really popular, and between 1990 and 2000, you start seeing a whole bunch of IGSM applications all around California, mostly California as far as I can tell. And they start adding different features, water quality, reservoir operations, Vado zone, subsidence tile drainage, so on and so forth, including the crop water demand. But since all these applications are propping up out there, and with the CVPIA, IGSM starts really coming to the public eye. But until 2000, it's a proprietary software, right? So nobody really knows what is happening inside the code. They just look at the results. And I think one of the things that they were having problems with is the stream aquifer interaction that IGSM was producing, especially with the CVGSM, the Central Valley Application Model. And that's when I start working with Department of Water Resources. I finished my graduate degree in UC Davis. I had no idea what IGSM was, so my supervisor said, well, we just acquired the source code. It's no longer proprietary, and there's some confusion with the results. Let's look at this and see if there's anything to fix. So that was supposed to be about a one-year project for me. So basically, I went through the entire source code. I still have those like 4 binders of like line by line. At this line, the code is doing this. At this line, the code is doing that. Very boring stuff. But I liked it. So anyway, so basically, we found some issues, fixed those issues, and we basically made a public release, and at the time we called IGSM 2 version 1. But at the same time, there was a peer review process of IGSM that was being wrapped up by Graham Fogg from UC Davis and Eric Labol. There was another master's student, unfortunately I can't remember his name, but they basically put together some hypothetical problems so that they can actually really study what the IGSM code was doing. And they literally ripped apart the IGSM. If you read the paper, they have a paper in groundwater, I think. They don't talk highly about it. So we fixed all that stuff. and we renamed it IGSM2, but all the way to 2005, every time we said, oh, IGSM2, people said, oh, yeah, IGSM, that model that just doesn't work or give bad results or whatever. So finally, in 2005, we said, well, let's just break apart from IGSM, the name IGSM, and we named it Integrated Water Flow Model, IWFM. And I think finally, people are starting to forget about IGSM, and we haven't had any issues with IWFM in terms of our results being funky and whatnot so far. Between 2005 and 2012, we started including enhancements to code. We included the zone budget, which in IDC you kind of started working with it. We included a second solver, which is faster than the original successive over-relaxation solver. We also included the time tracking simulations. Basically, IWFM is now time aware, and in our examples, you're going to see that. And slowly different applications started to pop up in California and Oregon. There's one in Oregon. 2012 and 2014, we released IWFM version 4.0. With what we now call IDC, improved root zone component. Original IWFM had a very different root zone component that C2V current C2V is using. We basically included in that root zone component rise and refuge operations. We are now able to explicitly represent those ponding operations. The original IWFM did not address those. We have now, improved code modularity. ModFlow is also, modular flow model, but we have, I think, a little bit, our modularity is beyond that in the sense that it's not, our modules are not IWFM centric. The whole idea is you can take these modules, turn them into their own executables, and then use them with other models as well, like IDC, both in an executable way and also in like a functional way where you can actually interact with IWFM at a code level. As the model is running, you can actually take information from there and whatnot. And more applications started to crop up in California. And then between 2014 and present, we now have IWFM 2015 with now full code modularity. We have included a whole bunch of different features. Kinematic wave, simulation of stream routing, ET from groundwater, so on and so forth. And we have also started using this code modularity idea to link IWFM or C2V at this point to different types of models, such as the reservoir system analysis models like calcium, if you're familiar with calcium. We have linked it to our agricultural economics models like SWAP. And we have also developed, different zone budget outputs for root zone and unsaturated zone components, mainly to support the sigma operations, because people are now very interested in, for instance, looking at C2V, especially the fine grid model, which we are also developing to zoom into their own areas and see not just the groundwater, but everything else, what is happening hydrologically in that zone, both in terms of water demands and movement of the water. And why did we overall develop IWFM? Originally, again, this effort has been going on since early 2000s, before Sigma even existed. And we basically developed IWFM mostly for the department's reasons. We wanted to better understand the historical evaluation of water resources in a basin. For us, that basin is Central Valley. We wanted to improve the accounting of groundwater, surface water interactions in a linked simulation reservoir system analysis model, which is, again, the result is calcium and C2V linkage. Again, I know there's a lot of acronyms going on here. C2V is our IWFM application to Central Valley. Calcium is, again, developed by Department of Water Resources. It's a reservoir systems analysis model. It basically looks at the downstream demands and regulatory needs and tries to figure out under different climate conditions and whatnot how the upstream reservoirs in Central Valley should be operated to meet those downstream demands. And one of our goals to develop C2V-SIM was to link the groundwater component of C2V-SIM to calcium. We wanted to study the impacts of climate change on long-term groundwater conditions and meeting the future water demands under those climate conditions with constrained water supplies. We wanted to address the complexities of planning and implementing integrated regional water management plans, and also look at conjunctive use projects, impacts of conjunctive projects. And again, we wanted to facilitate easy linking of a model like IWFM to other tools. So most of the time when you start looking at future planning in California, for instance, you can't look at the system, particularly the Central Valley, without looking at the reservoirs, how the reservoirs are operated. So that basically immediately brings the need to, linking an integrated hydrologic model to a reservoir operations model. And some people are interested in the economic impact of, for instance, the past drought. What was the economic impact? So they want to take the information from IWFM, groundwater-related information, and put it into an agricultural economics model and see what the impacts of the drought was. Or to go into the future, they want to see, what do we think the farmers will plant under certain climate conditions, under certain economic conditions. So that was one of the reasons why IWFM is what it is today. But of course, a lot of these things also nicely fit into the needs of Sigma. So IWFM, because of its design, we think that it fits nicely into the Sigma process and can be used as a tool by the GSAs to develop their plans, sustainability plans. So this is basically kind of a simple picture, kind of describing all different components of IWFM. What hydrologic processes we simulate within IWFM. At the core, we have the groundwater module. As you heard, Yang Yun started this as a purely groundwater model. So at the core, we have the simulation of the groundwater module. You can basically simulate a complex system of aquifers. You can have multiple layers, hydrogeologic layers. These layers can appear and disappear within your model area. You can have confined aquifers, unconfined aquifers. We simulate stream flows, interaction of stream flows with the groundwater. If you have any lakes or reservoirs in your model area, we simulate the lake storage and the effect of the interaction of the lakes with the groundwater system. We simulate what we call unsaturated zone. We simulate the land surface and root zone processes. But I think, I used to say a unique feature of IWFM. It's not unique anymore because Mountflow have the farm process as well. But one important feature of IWFM is that we actually can simulate the urban and agricultural water demand, given the soil properties, given the crop distribution, farm irrigation, farm water management, and atmospheric, evapotranspiration and precipitation conditions. We can calculate the water demand, and we can start linking that demand to stream diversions and pumping, and try to figure out, where that demand is going to be met, from the diversions or pumping, and we can look at the effect of the pumping and diversions in the overall hydrologic system. So most of the integrated hydrologic models are descriptive, meaning, you say, these are my stresses in my system, and tell me where the water is going, how fast it's moving, where it is going, so on and so forth. On top of that, IWFM is a prescriptive model as well, meaning dynamically we can calculate the stresses on the system. You know, like we are now prescribing the stresses, you know, in terms of pumping, in terms of diversion. So it's both prescriptive and descriptive, and you can easily switch back and forth between the two. So for instance, in a historical run, most of the time you're going to look at your system in a descriptive sense, assuming that you know your diversions, you know your pumping. But when you start looking into the future for planning purposes, then you can run the model both in a prescriptive and descriptive sense so that, you know, it will basically tell you what your pumping and diversions will be. And once you know, put those stresses into your system, how the water will start moving within your system. It's an open source model, and it's a regional scale model. So, you know, like some of the things that you might want to simulate at a local scale or farm scale, we don't have that. You know, most of the methods that we develop, we try to look at, you know, large areas with, you know, hundreds or thousands of farms. And again, we look at groundwater and surface flow system as well as the interaction between the two. It is a tool that allows you to represent, you know, urban and agricultural water management practices and their effects on the water system. It's a planning tool. It's an effective planning and analysis tool because of this descriptive and prescriptive approach. We think that we have a fairly sound theoretical basis. It's extensively tested now. I mean, if you run, yeah, John.
It was your last slide that prompted a question. Your thoughts about business of regional scale versus localizing it to a specific, I'm thinking primarily stream interaction. Obviously, I can take a regional model, I can discretize it down nice and tight around the stream. What are your thoughts about telescoping and having a mesh refined model?
Yeah.
Around the stream?
I think for that, I think you can think about it as a model that you can really zoom in to a small scale in that sense. I guess when I'm talking about regional scale, I'm thinking more about the land surface processes, right? So for instance, if you have a farm and let's say you're using flood irrigation, we can't like simulate the movement of water in the furrows, you know, from the beginning of the furrow to the end of the furrow, you know. So that's the type of scale that I was talking about. So, you know, when we look at the land surface, we assume that these, you know, large areas, again, possibly having, you know, tens or, you know, hundreds of farms, are kind of uniform in certain ways, and, you know, we don't look at the micro scale of water moving, you know, through furrows or, you know, going through the pores of the, but in terms of, you know, stream aquifer interaction, I mean, even there you can talk about, you know, you can go to, you know, real small scale. But as far as integrated hydrologic models go, we can go down to a small enough scale that you can simulate stream aquifer interaction in a, I think, a fairly accurate sense. And that's one model being developed right now by the Department of Water Resources for Sacramento Valley to look at specifically to the effect of water transfers on stream groundwater interaction.
Any sense of the processing speed issue? Like if I pushed it down to 5-minute intervals, how would I do?
I mean, if you are just looking, I mean, it all depends on what processes you include in your system. I mean, if you're just looking at streams and groundwater, it would be faster. But if you start putting in everything else, you know, land surface and whatnot, there are multiple levels of iterations going on. So you can have long running times. Mm-hmm. Yeah, so that basically, going back to this, you know, almost everything in IWFM is an optional feature except the groundwater. One thing you have to have in an IWFM model is the groundwater component, but everything else is optional that you can turn off or turn on, and that's how we're going to work on our examples. You know, we're going to start from a simple groundwater model, and then we're going to start putting in different features, and at the end of the 4th day, we're going to have a model with all the features turned on. So that's how we're going to look at this. So yeah, you don't have to include everything in your modeling if you want to use IWFM. Okay, yeah, so it's extensively tested. We hardly ever get any bugs these days. It's, we think, well documented. It's available for free to the public. The source code and everything is posted on our website. We try to provide technical support as best as we can. We work with, I don't know, sometimes I don't see anybody, but we try to, both Charlie, my colleague, who is mainly dealing with C2V sim development, and myself, we try to basically help people out as much as we can. Now there's numerous applications at regional scale, particularly with the Sigma. Different models are cropping up in California. There's one application in Oregon. I hear that there's one in New Mexico and one in Idaho. So, but it's, again, because of our agency's playground. It's mainly a California-specific model, but there was one question, I think this morning, is it developed only for California? No, it's a generic model. You can apply it anywhere in the world if you have the data to support it. It's peer-reviewed at multiple levels. In 2013, there was a peer review process that looked at the time, mainly to C2V sim, the application. They compared it to CVHM and also Hydrogeosphere from Canada. And we also try to write papers, peer-reviewed papers, as much as possible, when the opportunity comes. So we try to, get some, peer review backing for the code. And again, it's linked to reservoir system analysis models such as calcium and agroeconomic models such as CVPM and SWAP. And we think that it's well suited for the for Sigma related issues. And yeah, I mean, I've been mentioning this. It's the IWFM 2015 is now highly modular and extensible, and it allows you to develop your model gradually, starting from a simple hydrologic, like let's say groundwater, and start putting the different pieces on top of it. And it allows you to kind of test your input files and whatnot. Yes, John?
Contaminant transport, you mentioned it earlier. I'm hearing, mumblings about it. You got anything coupled yet?
No, there's a lot of mumbling about that, but no. So I mentioned IGSM used to have a water quality module, but when we reviewed it, we took that part out because initially my office is not interested in the water quality in the Central Valley. It's mainly flow, but because of Sigma, there's now an interest building one in. So I think it's coming. I don't know when. But I think that it has always been in my to-do list. It's just that I couldn't find any backing, but now with Sigma, there's a lot of pressure, so I think, that's going to happen probably the next year or so. We'll start from a simple approach, I guess, and then, try to build it from there.
Can you go to density driven?
So I'm not a water quality person, but they say that don't do that at these scales. So I guess maybe we won't go there. Okay. Okay, so this is kind of, for those of you who might be interested in interacting with IWFM at a source code level, right? Like let's say you want to do some kind of scripting around it, and like maybe as the model is running, maybe get some information from it, or maybe feed new information into it as it is running. That this is a schematic for those of you who are interested in that. But basically, this is what I'm talking about in terms of being modular, highly modular. The the IWFM core is very simple. If you look at it, it's like 10 lines of code, essentially. And it basically, what it does is it kind of organizes the communication between these processes. We have the root zone package, solver package, stream package, and so on and so forth. And we have different versions of how to, let's say, simulate the root zone system. We have these different versions there, and all those different versions are hidden behind this general package. So it makes, for me, very easy, for instance, to take, well, okay, as a user, you said, well, can you build this feature in? And let's say it's just a simple modification to one of these versions. I just, can take this and, copy it and then build that feature. From my end, the development is really fast. But also from the users and in terms of, interacting with IWFM, this whole system can quickly be compiled into, modularization. So, basically this root zone component, for instance, is now called IDC, IWFM Demand Calculator, which about 3 weeks ago we had a 2-day workshop on that. And then this part is now compiled into what we call groundwater dynamic link library. It is dynamically linked to calcium. The surface water and groundwater is, interacting as an optimization model is running in calcium. So that's, one benefit of this modular programming. And on top of that, you can actually turn this whole thing into what we call IWFM Dynamic Link Library. And a lot of stuff is now starting to be built around this dynamic link library. So for instance, again, the pieces of this, so basically what this is a library of hydrologic functions that we basically organize in different ways to come up with what you're going to see today and the next 4 days as the overall IWFM. But we can also take pieces of it and link it to calcium, which is, again, some kind of an optimization model. We can link it to agricultural economics model. It's not done yet, but we want to link it to transport models. Graphical user interfaces, like we're working on ArcGIS build, a graphical user interface build within ArcGIS, and we are using this IWFM library, and WKW model, which I call who knows what model. So basically this system can be used for a model that currently doesn't exist, but will exist in the future, and they want to interact with the IWFM engine. For instance, an example is there's a company in Spain, it's called Hydromodel Host. They basically provide cloud services, so that basically you can distribute your model over the cloud and people can interact with that model using their web browsers. They're now interacting with C2vSim through the IWFM DLL and putting all that stuff, basically retrieving data from C2vSim and putting into the cloud to their own database. So that's one example of who knows what model or graphical user interface. Okay, so that's basically the end of introduction. Any other questions?